Okay, we've been talking about reflections for a while here, and the two properties that always occur when a point gets reflected over a line. I'm going to make some connections now to our world of geometry and how reflections can help us actually explain other shapes and symmetry. Okay, so I'm actually going to make connections to reflections and connecting that to isosceles triangles. So make sure you have your notes when you follow along with this video. Pause where you need to, write down what you need to. But anyways, make sure that you're getting this information. So let's take a look at the reflections here again. So I'm just going to recap the two properties that are always occurring here. When you have a point and a line of reflection and you reflect that point, where that reflection point ends up is going to be equidistant to the line of reflection, right? So we know that this segment, if we were to measure from point A to the intersection point of the two segments in line of reflection, and this segment here is going to be equal length. So we know that those distances that each point is from the line of reflection is equidistant, meaning these segments right here are of equal length. Okay? And then we also know that we have this perpendicular relationship, a 90-degree angle. Okay? So what we need to put in our notes, make sure that you understand this terminology here, what a perpendicular bisector is of a segment. So a perpendicular bisector of a segment, like this segment A prime, this segment right here, the line of reflection is the perpendicular bisector because it cuts the segment A prime into two equal sections, right? Two equal halves. That's what bisect means. Bi means two, sect means to cut. So cut into two equal sections. And perpendicular means this 90-degree relationship. So any object that is perpendicular to a segment and cuts it in exactly half is what's called a perpendicular bisector. So our line of reflection is a perpendicular bisector of these segments that connect our pre-image and image points. Okay, make sure you have that written down. Isosceles triangles are triangles that have two sides that are of equal length, or congruent sides, two congruent sides. Okay, so an equilateral triangle here that I wrote is a special isosceles triangle where the third side is congruent to the other two. So therefore all three sides are equal. So equilateral triangles are just a special case of an isosceles triangle, where isosceles means it's a triangle, a three-sided shape, that has at least two congruent sides. Okay, so what is the connection between the properties of reflections and isosceles triangles? So to make that connection for you, I'm going to start with our moth activity, which is this right here. Okay, so this is what you should have submitted a picture like this in a previous quest where you had measurements showing the bisect part, or both of the segments in each of these colored segments here, that both halves are of equal length, and the segments in line of reflection are perpendicular. So this line of reflection is the perpendicular bisector of each of these segments, and it would be true for any pre-image and image point in the picture. Okay, so now let's add a concept to that. What I'm going to do here is, in this box here, I have click or show isosceles triangle. So if I click this, here's what happens. For each segment, I took a point and I put it on the line of reflection. So take this pink segment here. I took some point and I put it on the line of reflection, and I connected a segment from the point on the line of reflection to the endpoints of that segment, and it creates a triangle here, right? So we know that these are reflection points. So all those reflection properties of equidistant, I can't write on this. Equidistant and perpendicular here are true, but now when I add an extra point on the line of reflection, or this perpendicular bisector of this segment, the distance that this point is going to be equidistant to the endpoints. So the distance this point h is to g and h is to g prime is going to be the same length. And if I grab my measurement tool and I measure that distance here and here, notice we get the same length out. Okay, this blue segment here, same deal. I took a point, put a point on the line of reflection. Okay, and I showed the segments connecting that point and the endpoints. And what happens is this creates an isosceles triangle because of symmetry. If you think about it, this line of reflection is cutting this triangle in exactly half, right? Cutting this in half to where we could take this half of the triangle and reflect it so that it would map onto this half, which means that these segments are equal in length and these segments are equal in length. And even angles, when we reflect, angles are what we call get preserved, meaning when we reflect this half onto this half, the angles stay the same. So what we actually have here is, and I'm going to use my polygon tool, I'll make it blue. I'm going to actually make this half of the triangle. Notice it's kind of it's filled in with a blue color here, and I'll make it a little bit, I'll make it stand out a little bit bolder here. Let's turn the occupant. Okay, so now we got this half here, right? And all I'm going to do is I'm going to select this polygon, this interior here, and I'm going to reflect it over our line of reflection, and notice it reflected to this half and it covers it exactly. So each half here is congruent, which means these segments then are congruent, right? So when we put a point on the line of reflection or on a perpendicular bisector, that point is always going to be equidistant to the endpoints. Another way of saying that is we're always going to make an isosceles triangle, okay? And that's always going to happen with reflections. So let's take some notes on what's called the perpendicular bisector theorem. Okay, so we're talking about a perpendicular bisector of a segment. Okay, what a theorem is. What is a theorem? A theorem is a fact or a property that has been proven to always be true. So this perpendicular bisector theorem is just a Greek math word, meaning this statement will always be true no matter what. As long as we have the given information, this will always be true. So please write this in your notes. The perpendicular bisector theorem, I'll make this a little bigger for you. I don't know if you can see it in the video. The perpendicular bisector theorem says, given a segment and its perpendicular bisector, any point on the perpendicular bisector is equidistant to the endpoints. Okay. Okay, let's illustrate this perpendicular bisector theorem here. So what it says is, given a segment and its perpendicular bisector. Okay, so I'm just going to use the pen tool here. And I'm just going to sketch a segment. So here's an endpoint. Here's some line segment that connects, say, this endpoint. So here's a line segment. So given a segment and its perpendicular bisector. So I'm just going to draw a line or a line segment that cuts this segment in half. So say the midpoint would be somewhere like right here, which means that this half is congruent to this half. That's the bisect part. And then perpendicular means I need to draw a 90-degree angle, right? So pretty close here. So 90 degrees, right? So this line would be the perpendicular bisector. So what the theorem says is any point that's on the perpendicular bisector, maybe this one right here, is going to be equidistant to both endpoints. So if I were to draw the two segments there, these would be of equal length. So I got to use a different congruent mark because we're not saying they're congruent to these segments. They're congruent to each other, just different. So we just add a second congruent mark. But that's all that the perpendicular bisector theorem says, and that's how we're going to connect reflection properties to isosceles triangles. Okay? Here's an example of how we can use this perpendicular bisector theorem. Here's a picture I took of, I didn't take, I got off the internet, I took it from the internet, of the Leaning Tower of Pisa. Okay? So this building is famous because of its design, how it's sinking or whatever, and it is leaning to one side, right? So the fascination of this building is really because of symmetry. All of our buildings that we make are perpendicular to the ground, right? If you look at this building back here, or think about any building that you know, they should be straight up and down, right, from the ground here, and this one isn't. So let's use that perpendicular bisector thought with this illustration. So what I'm going to do is grab my point tool, and I'm going to get some points on this bottom here. So what I'm going to do is put a point on each side of the base of this Leaning Tower of Pisa. Okay. Now what I'm going to do is connect these 2 points with a segment. So here is our segment. So perpendicular bisector theorem says given a segment, then any point on its perpendicular bisector, a line that is going to cut this in half and go straight up and down, is going to be equidistant to each endpoint. So what I'm going to do first is, if I put a point up here right in the middle, right, of the top of this building, because it looks like it's a symmetrical tower, right, it's just leaning. So if I put this point here, if this was truly straight up and down, and that means that I can draw a segment that connects that point up on top to each endpoint, and that distance, or these two segments then, would have to be equal length, right, if it was truly straight up and down, which would make an isosceles triangle. So I'm going to measure the distance between these points here, and it looks like, oh, look at that, they're not the same, right? Therefore, this point E is not on the perpendicular bisector of this segment down here at the base. Okay? So I'm going to use GeoGebra's construction tool here, the perpendicular bisector tool, and I'm going to actually construct our perpendicular bisector of this segment. So I hope you can see this green dotted line that showed up. I'll hide the picture now, where this green dotted line is the perpendicular bisector of this segment CD. And notice that point E, that is the centerpiece, the top of our Tower of Pisa. Notice it's not on that perpendicular bisector because its distance is not the same to the endpoints. And that's how an example of the perpendicular bisector theorem and how we can use it. Now check this out. If I take E and I move it to the perpendicular bisector, notice our distances. They now become pretty much the same, and it depends on how good I can get. There we go. So now we got these to be the same, right? I move the point E on that perpendicular bisector. But if E is not on that, notice our segment lengths aren't ever going to be the same. Therefore, we will never have an isosceles triangle unless that third point is on that perpendicular bisector. Notice it forces an isosceles triangle. So that is what our perpendicular bisector theorem is talking about. If you have a segment and you have a perpendicular bisector, any point on that perpendicular bisector will be equidistant to the endpoints, which forces an isosceles triangle. Okay? Now, more generally speaking, let's see here. Sorry. I thought I had an isosceles triangle here. One way we can use this too, just give you an example. I'm going to make a isosceles triangle with a tool here. So there's an isosceles triangle. Okay, maybe I'll even change its orientation. We don't need the base always to be like the bottom of it. So looking at this triangle here, let's use our congruent marks to denote which sides are congruent. So this side and this side. So what this is actually saying too, and how we can use this property, if we're given an isosceles triangle, and I draw a line that goes through this point right here, and goes through the middle, hence the bisect, the middle of the third side, this segment right here that connects the vertex in that point. So since it's the midpoint, we have the bisect property, right? So we know that this segment is equal to this segment because it's the midpoint, the middle point of that segment. Therefore, that picture looks just like these pictures, and we know that that segment has to be perpendicular, right? Because we have two congruent triangles. This triangle here can reflect onto this triangle here. Okay, and there's those are some pretty big and important properties of our isosceles triangles. Another one to mention too is that these two, what we call base angles, down here, because of our reflection property, those are going to be equal in measure, meaning whatever this angle is, this angle has to be the same thing in an isosceles triangle. So in an isosceles triangle, we have two sides that are equal in length, and we also get two angles that are equal in length, and it's all due to our reflection property, right? And if we didn't have that in here, we wouldn't really see that property so much. But once we draw our symmetry line, we can see congruence, and we can now talk about parts of the triangles that are congruent as well. Okay. So here's how we can kind of think about this logic here. We got construction logic. How can I construct an isosceles triangle? Well, all an isosceles triangle is a triangle with two congruent sides, right? So if I construct a circle like I have here, any circle, and I draw two radii, which means segments that connect the center to a point on the circle. So here's one radius, and here's a second radius. And since they're both radii of the same circle, they have to be equal length, right? That's how circles are going to help us construct congruent segments. We're going to use radius concepts to get congruence. Okay? So this has an isosceles triangle, and I made the third side between these points dotted just to denote it from the non-congruent side there. Okay? So this is how constructions can help us always construct an isosceles triangle if we use geometric properties, right? Also now, if I draw a perpendicular bisector of this segment here, notice it goes through that point, and here's our picture, our symmetry in isosceles triangles, where this left half here is congruent to this right half, which means angles and segments and all that good stuff are also congruent because they would just fold right on top of each other. Now, this other side over here, I wrote not necessarily isosceles, thanks guessing, because if you just try to construct segments that look like they're going to be isosceles, it's really hard to get exact, right? So I can try to move these around and try to just line it up until I get these segments to be equal length, or I can just use properties that we talked about. If I construct, so maybe I'll use my construction process. If I construct the perpendicular bisector of this segment, I'm going to make a circle centered to F that goes to G, and I'm going to reverse that. Okay, so now I can see my two intersections of my circles, so I know that my perpendicular bisector is going to go through those. So that cuts that segment in half. And again, just like before, if I move E onto that, hey, look at that. We don't have to guess anymore. As long as E is some point on that perpendicular bisector, pretty close right there. Pretty close. It's on there. If I can get it exactly on there, then we don't have to guess on side length. So just showing you how our properties of geometry that we're learning forces relationships that we want. We're guessing just because something looks like it might be good doesn't guarantee us that it will, and guessing can actually be harder, but that's why we have properties. Okay. That's all I got for this video. The next video is going to show you how we can construct a reflection point and also a line of reflection. So thank you guys. Make sure you got all those notes there on our isosceles triangle properties and the perpendicular bisector theorem. Thank you.